And then the Lindler catalyst is okay up here. We talk about, oh yeah, okay, so syn addition. So which part of this parts?
Like normally on the test it appears as like, the diatomic hydrogen and the Lindler, and like I know that for the diatomic
H2
hydrogen
only.
it's always like syn addition, but I just don't understand what the Lindler catalyst does. Like
Um,
I don't,
so
yeah.
it controls the reaction so it doesn't go further than what you want it. So like
So it
PDC,
doesn't change the fact that it's just an addition of two hydrogens.
no, it's still so it it still occurs on the same side, so it's still going to be syn addition, but it prevents it from going further down the reaction line.
Okay.
That's
Okay.
literally it. But yes, it's still syn addition.
Okay.
Because you see, like, so this is an example of there's two different reactants that do the same thing, but one will continue to PDC will take it all the way home. So it will react with every single bond to take it all the way home, right? It will not stop at your double bond, but your Lindler will. Your Lindler, so if you don't want to get rid of your, like, for example, if you have, like, you know, there won't be a reaction here with your Lindler. You will keep your alkene here versus here, right? Because you're starting with a triple bond here, right? So it'll
Yeah.
only react that first time. So if you do not want to reduce all the way to an alkane, then you
Hmm.
use the Lindler. But
Okay.
if you just want to, run it all the way through, then you use your H2, your PDC.
Okay.
It's just a way.
Okay.
It's another way to control the catalyst, the not the catalyst, the reaction.
Okay. And then with the okay, wait, so then how does that differ from the one that's H2 and then comma PD slash C?
Yeah, that is this right here. You mean
Yeah,
PDC
so
will
that
PDC will PDC will run it all the way. It won't stop. It will not stop at
okay.
your alkene. It only stops once you get rid of all double bonds. It will just keep adding hydrogen until there's nowhere left to add hydrogen, essentially.
Okay, I got it. Okay. Okay.
Yeah. See,
Okay.
there
And
it
then
cannot be stopped after one addition, and the alkene formed in the first step will be further reduced to an alkane.
wait, and then is the one that's like the methoxyl or whatever or
Mhm.
OME, what is it?
Mhm.
Methoxyl is okay. That one, it is that a bulky base or not?
No. Um,
So then that's just does the regular but so is the N is the sodium methoxine or methoxyl whatever that is,
this.
that is simply if you have that as a solvent, that's just going to act as your base that's going to deprotonate and then the mechanism continues.
Yeah, let me see where. Let me see. Is this before? No. Let's, mhm. Yeah, someplace close. Is this also an alkenes, or I'm just gonna
Um,
say I don't see it in alkenes. That's why I'm asking.
let me see.
Is it alkenes? No.
Yeah, it's in the first summary sheet from retrosynthesis, so I guess that means it's introduced in like the first week.
Retrosynthesis summary reactions.
Yeah, it's in there.
HBr, HBr roar, BR2, NaOH.
It's on
Never
page
know.
15.
15. Oh my gosh, I didn't even see all this over here. It just keeps going, doesn't it? Yeah, so third degree with non-bulky base gives states of alkene. Yeah. Yeah, so remember SN2 does not
Yeah,
react with a third degree. Yeah, exactly.
Is there a good way to remember these things? I think I just can't memorize them.
So remember what is if you have a protic or aprotic solution, right? That's how you know if it's SN1 versus SN2, right?
Right?
And
Yeah.
then or E1 if you know rather if it's 1 or 2, let's just say that, right? So protic is for the ones, aprotic is for the twos. So in this case, NaOMe is aprotic, right? It's this right here, right? Aprotic, right? And then I typically look at like what is where would the reaction happen, right? Is it like a first degree, second degree, third degree? In this case, it's obviously a third degree. We know that third degree is not going to happen with a substitution, so it has to be an alkene addition. And then because it's a non-bulky base, it will be Zaitsev because the only time that you have anti-Zaitsev is when it's with a bulky base, and bulky is typically going to be your T-butyl or bigger. So
Yeah.
OMe is not that big.
Okay. Okay, and then the one that the sodium, comma, NH3 with the like thing in parentheses.
Sodium, NH3. Is this on the same thing?
It's not in that summary sheet. Let me see if it's in the next one.
Is it in alkynes? Let me see. Sodium, NH3. Oh, and then an L or an I or whatever. Yeah, this is an alkene, alkyne to an alkene.
So when do you know to use this?
Cis versus trans. If you want a cis bond or if you want a trans bond. So your NaNH3 will be your trans. Let me see, where did I put these summaries? I also have kind of notes that I made for this as well. Let me see. I know I put the summary on here. Okay, here it is. All right, you ready? We'll go through them.
Yes. Yes.
So, like, please. All right.
Yeah, I literally am like that.
All right, let me see. Let me get some of my stuff out of the way so I can write. My desk is full of crap. Okay, so this is when you want to create a terminal alkyne, right? Excess is the key here, right? These
So how do you wait? So how do you know? Do you have hints for like how do you know that by looking at it? Like, is there anything you think of when you see that like excess whatever that tells you, oh, terminal alkyne? Or
well,
is that just
excess NaNH2. This is this is going to be like when you have these BRs here, that means you're going to have multiple reactions. And so if you didn't have excess, then it would only react with one of them, and then you would get an alkene, right? So when you see excess, you know that you're going to do multiple reactions. So both of these are going to react. So this one's going to add a bond, and this one's going to add a bond, which is how you end up with an alkyne.
Oh, I
So
see.
yeah, so if your target molecule has an alkyne on the end of it, right, then you have to write excess, because if you don't, it's assumed to be just one worth of it.
I see. Okay.
Yeah.
Okay.
And then this is obviously just, you're just, turning that you're turning this back into your acetylide, right? But this isn't anything crazy, right? But these two are ways that you go from, and remember, Lindlar, that's the key here. You have the Lindlar catalyst where you're going from an alkyne to an alkene. The difference here between these two, if you only want to drop one bond, is your Lindlar is going to create your cis, right? And NH3 is going to create your trans. And we see that here. And we're talking about where the hydrogens are added to, because that's what we're doing. We're adding the hydrogens. And then over here, we've got these, right? But, obviously this is why we call it cis and trans, right? This. But remember that in these reactions, we're actually adding the hydrogen. So it's where you add the hydrogens that create the cis or trans version of it. Does that make sense?
Yeah. Yeah. And just going back to the second one for a second with the acetylide or acetylide one. Yeah. So does that like NH2 always just create the acetylide? Like is that just its whole function?
Yeah, you're basically deprotonating this and it's going on here and it's knocking this off, so this becomes a positive ion and then this is a negative ion, and that's how with its loose, and so that's why I wrote plus NH.
So that's its only function. So if you don't start with the CH3 bonded to C triple bonded CH, then beyond that NH2 doesn't have a use case.
Yeah, this is literally to create function of an alkyne, excuse me. So we can't do anything with this alkyne. We can't add it to something. So say you wanted to like add this to another molecule,
I
you
understand.
have to peel this apart first.
Yeah,
so that you
okay.
can make it react,
I see. Yeah. Okay.
So yeah, so those are our Lindlar catalyst. So those are, when we want to just break it one time, right? Then we use, depending on what we want to come out of the other side of it, right? We'll use NaNH3 or the Lindlar catalyst. And then these are both adding a bromine to your, where are we right here? These are both adding a bromine to your alkyne. I always get these all. So, but this one is going to add Markovnikov. And this one, see how we have two, we're literally, see one equivalent versus excess versus two, right?
Yep.
Let me just highlight.
Yeah, and then that one adds anti-addition, right? So to reduce steric hindrance.
Yes, yep. Yes, let me see. So this is just two BRs that go on there. And that's Markovnikov. We're adding it to this, which is equivalent to this. Right? So that's that there. And then we have these are both addition of water. Right, so
How do you know though that the bromines are gonna add on the carbon on that side rather than the other carbon?
Because of your and this one breaks it down. Oh yeah, it too. Yeah. Most stable anions.
Okay.
So it's gonna, it's gonna be your most substituted, most substituted.
Yeah.
Because obviously this side is not, that's a primary. So
yes.
So your hydrogen is going to get added to that side. And then so both of these are addition of water. So these two down here. So the difference between these two is one is going to give you your ketone. It's going to go all the way, oxidize all the way, and the other one is going to give you your aldehyde. Let me just change colors here. So this is giving you your ketone. This gives you your aldehyde. Because with this one, you're going to add, you have a hydrogen that's added here, and here, and here you just have it added here, right? And so that's where you end up getting this hydrogen here, but you end up adding your water there, right? So sometimes sometimes you will not be specified. So you might, what they're trying to say is like, sometimes you will not see water on there and you will just see HgSO4 and H2SO4. It's like, it's an assumed, because it's in an aqueous solution, right? It's an assumed part of your, reactants, right? So just be wary of that. Like if you might not see, like you don't down here, you don't see water down here. But just knowing that these are addition of water, right? So, and you see this mercury or, your BH, whatever, THF, that's all addition of water. So one is going to be, you're going to have your aldehyde, which means you're adding it to your end terminal, the end of your carbon chain, versus your ketone, it's going to be on the inside. It's going to be added on this side. And then these ones we have, because this is anti-Markovnikov, just to make that anti-Markovnikov.
Due to the peroxide, right?
Yes, exactly. Yep, exactly.
Okay,
Yep.
so you know that you're adding the water due to the fact that it's in solution. Like, is it like, is
So
that
this
where
is,
the OH and the H are coming from? Because like
you mean
nothing
in
in
the final
there, like,
product?
yeah.
Yeah,
Like, how do you
so,
know that's addition of water by looking at it?
well, some things you just have to know, my friend. These are these reactions are used to add water across the bond, across the alkene or alkyne, right? But because we do it, but we use, when we add it to, right, when we add it to an alkene, we use HgOAC2. But we don't have, because that doesn't work well enough on an alkyne, it doesn't have enough energy to break the bond or whatever. We have to use HgSO4 as our catalyst to get that water to go across the bond. So I would say that if you feel comfortable that in the fact that like if you saw like it's if you felt comfortable in the fact that like when you saw that reactant or when you saw that there was water added across an alkene, and you could tell that if the alcohol was added to the least substituted side versus the most substituted side, that you knew which reaction it was. This is basically the same exact thing. We're doing the same exact thing, except we're adding the water to an alkyne.
Mm-hmm.
So that's literally the only difference, right? Is like we're doing the same reaction using generally the same reactants. I mean, they're at least comparable. They're somewhat similar. They're not totally different. We still have the BH, THF, right? And the peroxide. We still have the mercury and H2SO4, right? So they're like kind of similar still.
But then why is but like if you're adding water, I thought you would be adding like an OH, but you're getting a ketone. So are you adding an OH and then at some point it gets deprotonated?
Yeah. Yeah. So you are adding your water across here. So you have your H and your OH, and then you deprotonate your oxygen to create this double bond with
Yes.
the
Okay.
whatever it is. Yeah.
Okay. All right.
And then these are all on how to increase your chain, right? So that's all these do. This is basically like if you had
Yeah,
this,
and they just attach on.
yeah, you would
Yeah.
do this and to give yourself this, and then you would, whatever it is, you would either, you put the bromine or, all these, right? So if you wanted to do these things to then increase your chain, right? This is just
Yes.
increasing your chain in different ways. So that's all that those are. That's all that. So it's just that all just depends on, and this is both
So then
um
how do you know that you are using the hydronium ion? Is that for the uh protonation deprotonation purpose?
yeah. A lot of times when you have that H3O plus, that's exactly what it's for. It's your like what's considered like your acid workup step. So it's how you end up putting your, because you'll have an ion somewhere, right? And so you need to like reprotonate it, deprotonate it to stabilize the reaction. With
Wait,
SN2,
can you scroll up slightly so I can take a picture of it?
oh yeah. This is the whole thing.
Thank you, because this is the master sheet.
Yeah. No problem.
So you gotta get the picture.
Yes. And yeah, this is, let me see, I'm trying to see if there's any other little, um,
Yeah.
yeah, so SN2 reactions, obviously you don't have to have that like acid workup step, right? But when you're doing stuff like this, here you're adding it directly, it's directly attached um to, so you're because remember you're attacking right here, right? So it's directly
Mhm.
attached, that's this carbon here. Um Other reactions of acetylides with and epoxides. Yeah, so yeah, this is basically just saying like when you have that C double bond O, right? Or epoxides, which is this right here, same reaction where we're attacking right here. And then we just have to have that acid workup step um to protonate, you know, or deprotonate or whatever, but to protonate our oxygen. So
Okay. I don't mean to be a pain,
no, you're fine.
but can you maybe do the same exact thing for alcohols?
Yeah. Yes, our alcohol reaction. Let me see. Let me see. Okay, how far down was this one? Do-do-do-do-do-do.
Because you know what, honestly, these sheets are like gold because I feel like trying to like glean all this from like the gap notes
Yeah.
is
Yeah, I get
challenging.
it. Listen, that is what I spent a lot of time trying to figure out these little patterns. So I totally get it. It's not fun. Not fun at all. It's yes, you can totally skate on my, what do they call them? Coattails for this.
Yeah, sorry.
Yeah. No, it's all good. It's all good. That's what I'm here for, right? Um, Mild versus strong. Oops, sorry, I'm spelling strong wrong. Strong. So these are your reduction reactions. Your reduction reactions. So these are both, so this will react with, they will both react with, I will say, ketones and aldehydes, right? And this will also react with ketones and aldehydes, but this will also react with ethers. So, oops, I should probably say ester, not ethers. What am I doing? Esters, sorry.
Wait, when you say mild and strong, what does that mean exactly?
Yeah, like the their like their abilities to react, like how strong the base is, right? Like how strong it will, like lithium is stronger in the reactions than it is than sodium is, right? So it can react more with more functional groups, right? So this is supposed to, let me fix this. So this is ester. I'm just gonna, okay, here. Right, this is an ester. You're able to move it through to an alcohol. So these are just reducing agents. So NABH4 is less, it's a more mild reducing agent, right? Versus, especially, again, notice that we have excess here, right? So we have the word excess, so that we know that it's going to go through all the way to reduce it into this alcohol. So that's all that is. We're reducing the amount of bonds to the oxygen. Remember when we right, like redox reactions, right? We reduce or oxidize. When we oxidize, we're increasing the bonds to oxygen, and when we reduce, we're reducing the bonds to oxygen, adding hydrogens, right? So that's all that means. So we're reducing the number of bonds to the oxygens, right? And this one will, yes, go ahead.
Wait, but how do you like get rid of the oxygens?
Yeah, I was gonna say this one will like literally peel it off. Let me see where they have an example of it. I'll pull it up for you. Let me.
Because the hydronium again is doing the protonation, deprotonation, and then for the, what is that one? Ethyl oxide in the first one.
Yeah.
So how does that work, or what is that doing?
Alcohols. Hang on, I'm gonna bring it up for you so you can see it. So these are complicated. Let me see. This is all about your ring stabilization. Okay, so preparation of alcohols, hydride reductions, that's this stuff. Those are alkene reactions, which we did. Okay, here we go. So page 7. 4.2. Okay, here we go. This is really, so alcohols can be made by reducing the carbonyl, right? Reducing the functional group. So the hydride anion can't do it on its own, right? So what we do is we have these, we have to use these. So right here, sodium hydride, very reactive, right? Lithium, right? Less reactive, more useful. But sodium borohydride is least reactive, most selective, right? So it's going to, you have your decreasing electron paired energy, right? So what we're doing is we are attaching through this, remember we have this dipole, this carbon here, and which will peel the electrons off of that, and then this is what we use to make our alcohols, right? So we're adding the hydrogen. So the hydrogen, because again, this guy is okay with being, and so that's how we get our hydrogen comes onto here. The hydrogen peels off. And then because we have all these electrons on this side, we deprotonate our OET, and that's how we get our reduction, right? It's an addition reduction reaction, right? And so it's the same thing with, so these ones here, so here, yeah, this is how, so the less reactive sodium borohydride, right? It reduces everything, but it does not reduce esters. It can't reduce esters. You have to use your lithium because it will peel. Let me see, the more reactive, the complete removal. Yeah. So does it have I wanted to show you the mechanism though. Okay. I don't know if I actually added the mechanism on here, but I'll draw it out for you. Okay, so this is what the mechanism looks like, right? So we have our, right, and then we have our ester, right? So let's just put OMe. Okay, and then what's going to happen is our aluminum comes in, and we get this hydrogen that attaches here. Just to be clear, we have a negative charge here, right? And so this hydrogen attaches there, which gives us, this is our addition, right? And then because these are, you know, addition elimination reactions, so then because we have, this is an O, this is an O, because these electrons obviously get kicked up here, right? And so what happens is when this comes on, and then we have, you know, Me, which we can just leave like that. We don't have to write Me. So then what happens is when these come on, these electrons come back down. Whoa, what's going on there? These electrons come back down to create the double bond, which then kick these off, right? So it kicks, because it's not going to kick hydrogen back off, but oxygen is happy to carry the electrons. So then what ends up happening, whoopsies, is we have this, because it's an aldehyde, we show our, and then plus, right, and it was Me. So that's what ends up happening. So these electrons turn around and want to create that double bond. So that's how we reduce, how it reduces to the aldehyde. So then what ends up happening, so then from here, what we do is another one comes in. I don't know if I drew them the same color, but hopefully you get the point. Another one comes in, and it does the same thing all over again, right? And again, this one's negative. And so it does the same thing all over again. So then this 1, 2, 3 becomes, and then pop up here, right? Over here like this, and now we have our 2 hydrogens, right? So these are now the 2 hydrogens that have been added, and then we have our, remember we have our acid workup, right? So, and then what happens is H3O plus, I'm not going to draw it out because I don't have room, but so what happens is it peels, it'll peel a hydrogen off of there, whoopsies, which will give us this. And then remember, we have our 2 hydrogens over here as well, but you don't have to draw them in. So then this becomes our 1st degree alcohol, right?
Okay.
I know it's kind of like crowded and everything, but hopefully, so it basically just reacts
It's
twice.
good.
Yeah, the first time it kicks it off, the first time it kicks off the 2nd oxygen of the ester, and then the 2nd time is when it turns it into an alcohol.
Yeah, okay. Yeah, see, I mean, like, I went through all of this stuff in the notes. I just can't remember any of it. It just
That's
leaves
okay.
the brain, and like, I can't even, like, yeah.
Yeah, no, it's all good. It's all good. Just remember that, when we have those, like, a lot of this stuff kind of goes back to the donating groups, right? What's a strong donating group? What's a weak donating group, right? And so, where some of those reactions are going to come from, aldehydes and ketones are like, they're weak donating groups, so the carbon oxygen bond is going to be like more reactive, and like this bond here is going to be more reactive, so it's going to be come in there.
Okay.
Yeah.
Wait, can you
And
go back to that other the summary page?
Yep, I can. So let me see. So I guess stronger and weaker is what I should say is like less reactive, more reactive. Maybe that would be a better way to say it for you. Less.
So how do you know? Okay, so because the first two can basically make an alcohol out of ketones and aldehydes, how do you determine which one you use? Like given a ketone.
Yeah, like you could use either, really. You could use either. The thing to know is that NADH4 will not react with an ester. That's just the biggest thing to know. Is like if you
Okay.
want it to react with an ester, you have to use excess lithium aluminum hydride or whatever. But otherwise it doesn't matter.
Okay.
Either one is acceptable.
Okay.
Yeah. And then
The
let me see.
PCC, that one's just making the aldehyde, right? Or we
Yeah.
know. Yes.
Mhm. Yeah, so this
Okay.
is again one of those things where like you're only going through like one time, right? It's only one reaction for like a first degree to an aldehyde. So it's just one time that it's happening.
Wait, so it can only be a first degree.
These are, yeah, yep. So these, let me see, these three are oxidation reactions. So we have our reduction reactions where we're going from the double bonds to the single bonds. And these are our oxidation reactions where we're going from the single to the double or whatever to oxygen, right? So remember, we're oxidizing, we're increasing the number, right? So, and again, this would be an example of like what's considered mild, as in it's only going to happen one time. Whereas like these are your examples of strong, right? Which they're literally the same thing, but strong. So they can happen multiple times. So in this case here, this is a first degree and this is a second degree alcohol, right? So
But do they have to
this is
form any?
first degree to an aldehyde. Sorry, go ahead.
You know how for the PCC goes to an aldehyde? Does the second one, the one below that, the chromium one, or the both chromium ones, like it looks like that second one is a ketone, and then like do they have to form anything specific?
So it just depends on where the alcohol is. So in this first one, we're going from an alcohol to, I don't have any room. So we're going,
Because isn't that a carboxylic acid?
that's right. So we're going, in this one, we're going from an alcohol to an aldehyde to, like you said, a carboxylic acid.
How do you know that the aldehyde is the? Oh, right. Okay, it's coming back to me, right? Because like
Yeah.
the aldehyde is like the intermediate thing. Like it like
Yes.
goes in steps.
Yep.
But then there was that one that said like sometimes it stops prematurely. Like if you don't want to go all the way to the carboxylic acid, you can stop the aldehyde. Which one is that one?
Yeah, that one, that would be for the PCC. That's where it will only go to, see, that's the difference between these are both first degree.
Yeah.
But if you only want it to go to an aldehyde, then you use PCC because it's mild, right? It only doesn't react as
Right.
much. And then for this one, obviously you're going, if you have a first degree alcohol with chromium, you will go all the way to a carboxylic acid. If you have a second degree, you'll go to a ketone. So this is obviously alcohol to ketone, right? And this one, these are both first degree, but this will only go to an aldehyde for PCC. So that's how you control the mechanism. Again, a lot of this stuff you're starting. Yeah, go ahead.
Sorry, I'm sorry. Wait, the third one, you just said it. I just like missed it. Wait, so you know how like the reagent is the exact same for the first degree and second degree? So the third one, the second degree one only goes to the ketone.
Yep.
Why?
Because it's only, it would have to kick to go to a carboxylic acid, it would have to like kick off that ethanol or ethane, ether. Like it doesn't have the ability to like add another oxygen here because it's already connected here.
Okay. I see. Yeah, because the first degree has more hydrogens to like substitute with something else. Okay.
Yeah, exactly. Yep. And then all of these are substitution reactions. And so it's literally just like whatever it is you're trying to substitute it with, right? See, whatever's in there is going to be in your product. Is going to replace your alcohol. You guys did not have to know, I think, either of these.
Yeah, I was just about to ask a question on that because on the test, one of the questions had it was substituting a chlorine. And one of the options was the SOCl2. The other option was the TSCl. And I think the other option was HCl. Can you break down when you can use the different ones?
I am going to follow up with her to just have her double check that the answers don't contain those, because that's not like, it was something she found out that you guys weren't on the hook for. So I'll follow up with her about that moving forward. So you said that the answers were HCl, TSCl.
Look at and figure out which one it was, because I think I picked the SOCl2, but I couldn't figure. Yeah, it's number 11. There were like 5 choices, like 2 of them didn't make sense, but then or 5 or 6, but the 3 that like were plausible were it was an alcohol, and then in place of the alcohol you got a chlorine. So
wait, was this for exam
was,
1 or exam 2?
Oh, it was for 2. Yeah, last night or 2 nights ago.
Yeah, okay, hang on.
Number 11.
Yep, let me get in there.
And it was a primary. So that's why I was confused, because then can't you use HCl or SOCl2?
Yeah, I was gonna say the biggest difference is SOCl2 is not for sugar, but yeah, if it's primary. Number 11. 13. Oh, what? I don't have a number 11 in here. Goes 8. Oh, 10. Oh gosh. Okay, 11. I see it now. So what's the major organic product? Is that the question?
No. It was like a drop down. It would just had like a ring, and then like there was an alcohol attached, and then it was the same ring, but then in place of the alcohol it was a chlorine.
Oh, it's like a ring. This is number 10 for me.
Oh.
But let me see. It's
It's a hexane.
Yeah, it's a hexane, but then it has a carbon and then the alcohol, correct?
Correct.
Okay. Because I have another one that's kind of similar on here, but let me see. Okay, so for, oops, that's not it. Okay, so you want to know what the difference between using, you said SOCl2 and what HCl would be on this one?
And TSCL.
TSCl as well? Okay. Okay. So let's see. I do not believe you definitely do not have to. OH. Oh, maybe that is on there. Okay, I was gonna say I think that would add more to it, but okay, so yeah, see, TSCl would also add the TS to it, so that's why that one would not work. Because it doesn't
Wait, how do
just
you know? Oh, I see it now. It's underneath on the summary sheet. I was like, what are you
yeah,
talking about? Yeah.
yeah, I
Okay.
was gonna say yeah, because that also adds the tosylate or yeah, tosylate or whatever it's called. Um, so that's why that one would not be a good one. And then the other one, what did you say, HCl versus
The
SOCl2?
yeah. Mm-hmm.
So with SO, see, this is, let me see. I think it has to do with,
Because it's not like it's a third
oh,
degree.
SLCl2. Oh, I see it over here. So another, oh yeah, thionyl chloride. Okay. So first degree and second degree alcohols are for the SOCl2, which HCl is not for third degree. Okay, I get what you're saying. Yeah.
But it's not a third degree. That's the thing.
Yeah, let me see. Here we have the let me see so the leaving group is going to be your Cl2. So it will work with SN1. So it was a primary, so it would have to be an SN2, which means that it would just do a substitution, which is this.
Wait, are
First
you
and
drawing?
second degree. No, I'm not.
Oh,
I'm
okay.
thinking and reading and trying to like figure out why, like what a good reason to choose one
Yeah.
over the other would be. Um, yeah, we know this. HCl will work in all of them, but in a primary, it's SN2 versus in a secondary, tertiary, it's an SN1 reaction. If it was on a primary, why would it be better to do that one though? Because in a primary, it's SN2 no matter what. It's, hmm.
Does it have anything to do with the fact that it's a ring?
I
Because on
think
the summary sheet, like, okay, I only picked the SO one because I just remembered that it looked like that on the page. And I was like, no, because like at that point I didn't know. So I just like
Yeah.
picked something but that's not even a reason.
No, I know. And because it kind of looks more like that one kind of looks more like this because there's this intermediate carbon here between the OH and the ring. But yeah, that's a good question. I'm not sure how to say to choose one over the other. In that case, it's a hexane with a primary alcohol on it. Because because of rearrangement. Duh. You'll get rearrangement with HCl. That's why like it works with, although with first degree though, I feel like I don't know if that's because,
Wait, how do you know it's getting rearrangement?
well, you would, but see, that's what I'm saying with the first degree, you wouldn't necessarily get that because it can do SN2 reaction. So that's why I'm
Right.
not.
Yeah. No, it's okay.
Yeah, that's a good question. I don't
I
know
just
exactly why. Yeah. Yeah, because yeah, for SN2 you don't have rearrangement. It's a concerted reaction.
Yeah, and then also the same question goes for like back to the summary sheet. The same question goes for the HBr and the
PB3.
PBr3 regarding
Yeah.
the difference. It's like the same concept as the other one, just for that. I don't
Yes,
know
exactly. Yeah,
when.
yeah, because this is remember it's these are like bulky, right? So like SOCl2 and PBr3, they're bulky, so that's why you can't do and they operate through SN2. So it's a concerted reaction. So you literally can't do it through a third degree, a
Mhm.
primary. I guess maybe it would be a question of what would be most likely to react the quickest, because a lot of these are as you get it, it's yes, those would both work, but what would work better? And I
So
know that's
what
kind
wor-
of
Wait, so would the bulky ones work better?
on a first degree.
Yeah.
I mean,
Because my thing is like the
you use a
HCl and
bulky base when you want to avoid using, when you want to avoid getting SN2 reactions. So if you have a bulking molecule, does that kind of bully the other ones out of the way, so to speak?
I
Dr.
don't
Bly
know.
used to say they were like sumo wrestlers. Like imagine them like sumo wrestlers trying to get through a doorway for the reactions. Yeah, I don't know. It might have to do with the size, or it might have to do with how good of a leaving group it is, because really what's happening um is you're protonating with these you're deprotonating this and then this chlorine, right? Um in this example, right? So you're deprotonating that, and then this becomes a positive, and then this can come over and can attack, and that's how you get this substitution reaction. But this isn't an SN1 or SN2 reaction. Obviously, that anion is cation, excuse me, is the most stable in that scenario, and that's why we don't have the rearrangements. But as far as when you're on a primary, I mean, that to me would be it says that it can operate, it says that HCl can operate as an SN2 on a primary alcohol. I'm just assuming that it probably has more to do with potential rearrangement, because that's the best thing that I can say is that it probably has to do with potential rearrangement, because it does have to work. HCl works differently than SOCl2. I'm gonna say H2OCl4, but that's not the same thing. So that would be my guess. That would be my guess, but it's a guess at best.
Yeah, no, and then you're probably gonna kill me, but
No, no, no.
um the organometallic or
Yep,
whatever
yep,
reagents.
Grignard.
Do you mind?
No, 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 not
Do
at
you see
all.
it, Sarah? Do you see a trend here?
We just go further and further back the more we talk. No, just kidding.
No, we're this is the last one before the actual this week stuff. And then
Yes.
but now I'm very disappointed because there's
Okay.
another summary reaction for the next one.
Oh no, there's some reactions. All I don't think you finished.
Probably every single one.
Almost. I don't even think. Let me see. Was there one some on aldehydes and ketones? Oh yeah, I'm pretty sure every single one we have a reaction summary sheet. Yeah, we do. Carboxylic derivatives. Although I will say, the further along we got in here, the less of my cool little cheat sheet stuff I have, because I was like dying by the time I got this far into OChem.
No, don't say that.
Have to go back through and find my find my patterns. Yeah, so okay, so Grignard. Okay, let's go. Let's see. This is the
There's
alcohol. I
only
was going the
6
wrong way.
of them this time, so it's not that bad.
Did you already take a picture of this? Do you need this or no?
Oh, I absolutely took a picture of that.
Okay,
Yes.
okay, cool. Yeah. Okay. I was trying to like figure it out. Okay, so here we go. Organometals. Yes. What about them? Good old Grignard. Okay. Conceptually, or what do you have questions on this one?
Yeah, so I just want to go over it. Like
Yeah,
just like do the same thing.
like from the beginning. From the top.
Yep.
No. Okay.
Because my problem is I do the gap notes and then I can't remember a single thing after doing them.
Yep.
And so
Yep, I know.
these sheets are kind of like necessary.
Yeah, no, and I get that. And also, I think I mentioned this to you before. Something that I started doing was I would go through and watch the videos, fill out the notes, all that other stuff, and then I would go back through and read the notes from the beginning and seeing myself filling these things out. And it helped to kind of solidify some stuff. So,
Yeah.
magnesium bromide, right? Less electropositive, so there's more covalent character, so that's why we use that as opposed to, say, sodium or lithium or something like that, right? So lithium smaller, it's more covalent, so
What exactly is electropositive?
the opposite
Is
of
that just the
electronegative.
opposite of electronegative? Yeah, that's it. Okay.
Pretty much, yeah. More willing to give up its electron density without getting mad, versus like the other way around, right? Like fluorine, oxygen, like they are very greedy. They want all of the electron density and yours and his, you know what I mean? So
Yes.
they're more of like a donator in that sense.
Mhm.
So when we're making a Grignard, right? It's just MgTHF. Good old THF comes up a lot.
Can you go over the Grignard thing?
Yeah.
So what is the distinguishing feature of that? I just like it kind of like
Of a Grignard reagent, it's literally this. This is literally the Grignard reagent. Like that
what
is
does it
it.
mean? Like what is it
Grignard is
it's
the
just a
name of
name?
the chemist that found this reaction in order to use this to create carbon-carbon bonds. It's just a really great, easy way, besides the fact that you have to keep it dry. Like if you react it in water, then basically you're screwed. But yeah, as long as you have a dry reaction environment, it's a wonderful way to create carbon-carbon bonds. That's all it really is.
So it
but the
has to
Grignard,
be MGBR
Yep.
or
Yep.
okay.
Yep. Mg is really like magnesium is really the big piece of it, right? Like you will see it with other, but like other halides, but you'll see it here with bromine. So, but you can like, use other halides, but for all intents and purposes here, you'll see it with bromine. So, but it's literally this, like you're literally inserting through a couple steps, you're literally inserting magnesium between what happens is like, it's like, because it's very strange to think like, well, how does magnesium just like add itself in there? Well, what happens is like bromine actually comes off and then magnesium goes on and then bromine goes back on. That's actually what happens, but we don't have to worry about the mechanism here. So yeah, so that's literally what it is. So yeah, and with water, it's not useful because what ends up happening is you lose the whole purpose of being able to use it. Because what happens, because this is more electropositive, right? So you have this, wow, partial positive versus partial negative on your carbon, right? And that's pretty rare, right? And so it's a great way to be able to react it with another carbon where, as per usual, it's a partial positive, right? Especially when it's attached to some other electronegative molecule. So then we get this reaction like that. That's the whole point of putting on this Grignard, is so that we can actually do something with it. So if we don't, if we have water in the reaction, all that's going to happen is we're going to protonate it. Because this is a partial negative, it's just going to pull this hydrogen onto it. But if we have it sin water, no water, right, then we can actually connect this to, as you see here, we can actually connect this to whatever it is, right? So because this has this partial negative, this has this partial positive. So that's why it makes it like a useful way to, as long as it's dry, it makes it a pretty useful way to start adding like your chains, right? And if you ever do the lab, this is like what you'll see. This is like your classic, this is your classic right here. But yeah, so we have this, this electron repulsion between these ones. So, so basically we're trying to figure out like what's our synthetic equivalent for this one, right? As an example. So we have our magnesium. So what are we trying to make? We're trying to make this right here. I'm like, where is it? So we're just trying to make this. So we, you try to figure out like, oh, where would I cut this, right? How would what's our, synthons and synthetic equivalents. I told you why I have a hard time saying this. But anyway, yeah. So when we want to like add on to our carbons, typically our, a Grignard is a great way to do that. So, and you can literally add whatever you want to your, you could literally have like CH3, CH2, CH2, blah, 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 MgBr. And, as like something that you are reacting into, and then you have to have your acid workup step, right? But, and you add that to it, and then you end up with this chain, CH2, CH2, however many I did, right? CH3, right? And so you can add this, like, this can kind of go on anywhere. That's kind of the point of it. You can kind of add it however many you want. So, and then here's your mechanism for it. This is your acid workup step. Anytime you see this, that means it's an acid workup step, which means that you are just protonating your whatever, alcohol in this case, right? But you're protonating to create that stable ion at the end. But you have to do it at the end because otherwise then it won't react, right? So we keep it out of the reaction until we're ready to end it, right? And then we cleave that interaction. So yeah, so this is it, and we see it here, right, with our partial positive on the magnesium and our partial negative on the carbon, right? And then this we already know is going to be a partial positive and a partial negative due to our dipole, right? That's all old material. And so this comes in and attaches to our carbon here, and so this magnesium pops off, magnesium bromide pops off, and we are adding from this carbon, so to the side of magnesium, we're adding that on. And that's what we see here, right? And then this magnesium bromide has a positive charge, as we see. and it attaches to our, now because we've popped our electrons on up here, our negatively formal negative charge of our oxygen. So, but this is a good leaving group. That's what makes this whole reaction go, is because this is such a good leaving group that it, you know, it'll come back off again. And so when we do our acid workup step, right, here it is, right? We do our acid workup step is when we're putting that hydrogen here on the oxygen, and the bromine, the magnesium bromide goes away. But yeah, and so that's how we end up with our final reaction. But the great news for you is you can just like assume the character, right? And so if you see that, you can just go, if you see MgBr attached to something, you can just skip right over to this, because you know all of this is going to happen, and you know, unless it asks for the mechanism. Don't do this if it doesn't ask for the mechanism, right? But then you can like just come right to this conclusion that whatever is attached to your magnesium is going to attach to the carbonyl, right? So that's the overall theme there. And so if you're starting with something, right? So very important carbon-carbon bond formation, right? So if you're starting with something like this, again, okay, I said most of the time you're going to see magnesium bromide, right? You do. But just remember, it's a halide. It doesn't matter what it is. It's a halide. Most of the time you will see it, but it's useful in all of the halide reactions if you need. If you have a different halide, it's not like you can't use the Grignard reagent, okay? So MgTHF, because what happens is THF will peel off the Cl, and then the magnesium can pop on there, and then the magnesium can pick up the Cl. So that's how it happens. It's not that it like literally inserts it in between it. It's just a multiple step thing that happens. And then, so that's how you get the magnesium on the inside as opposed to the outside, right? So just commit that to memory, unless you want to memorize the reaction, steps, and then you can, play it through, but nobody wants to do that. So then when we see this, we see this and we see this, we know that this carbon here is going to get attached to this carbon here. So remember to always count your carbons if you're ever unsure, right? So now we see that right here with this line, right? But this, this is still attached to our oxygen, and this magnesium hops over onto here essentially, right? So that's why we see this here. So now our magnesium is on the oxygen, and we've created this carbon-carbon bond. Okay.
Yes.
Then
yes.
we do our acid workup step, same thing. And just basically the magnesium chloride goes away and the oxygen becomes an alcohol. And that's why, and here we are with our new carbon-carbon bond, right?
Yeah.
So that's the mechanism, yeah.
Yeah, so in the summary page, when it has MgTHF.
Yep, all you're doing is adding, all that is you're creating your Grignard reagent. Your Grignard reagent literally is your molecule that you want to add to another molecule with the magnesium on it so that it can react.
I see.
So this is not the Grignard reagent. This is the Grignard reagent because this is what you are going to use with your Grignard, right? It's Grignard because it's the name of the scientist, right?
Yeah.
I think he was like a French chemist or something.
This is basically, the concept is just the MgCl is a good leaving group.
Yes, so Mg halide. Just think of it as a halide.
Got it. Okay.
But yes, okay. Because it's usually you'll see bromine, that's why. But you can use other halides as well.
Yeah, okay. So that first one is, just creating the reagent like you said.
And then, that's all you're doing, yep.
And then the next one is literally just using that reagent to make the new carbon-carbon bond.
This up here, this is what you're talking about? Yes.
No, I'm just looking at the summary page.
Sorry. Yes, summary page. Okay. Yep, on page 8. Let me just scroll down to it so that way, because I am recording too, so I want people to be able to see. Yeah, so exactly.
So then the second one's just using the reagent to make the new carbon-carbon bond.
Yes, exactly. So this first reagent, this first reaction, summary is how you would obtain this.
Got
And
it.
remember that this can be any halide, right? So
Mhm.
for all intents and purposes, like I said, you're gonna see bromine, right? But just know that if it comes up, it doesn't have to be bromine, right?
Yes.
So yeah, so MgTHF is just how you make your Grignard reagent if you don't have one yet. And
Mhm.
making a Grignard reagent is a great way, like when you get to these multi-step synthesis problems, and you'll see that like making a Grignard will come, 4, 5, 6 steps in, so that you can create these bigger molecules, right?
Yeah.
So yeah, so with our reaction summary, right? The first one here is we're creating our Grignard reagent. And then the next one is just showing how that happens, how a Grignard reagent would go on. And then,
Yeah.
so in this case, what we would have, see, there's no carbons here. So the only carbon is right here. That's not like a chain, right? It's not a chain of carbons, just this carbon here. So these two carbons are going to come together to create this bond here, which is going to leave us with a primary alcohol, versus the epoxide is going to give us that secondary alcohol, because remember, we're going to react here, right?
Yeah. Okay. Right. But I thought I thought for the epoxide, I thought it
Sorry.
was the lower left. So
Yes,
then,
sorry. Yes,
okay.
you're right. You're right. You're right.
Okay, I
It
actually
is.
did get something right.
Yes,
Shocking.
no, it is. No, that was my fault. Yeah. Yes, you are. You're creating that. Yes, and that's this here and this here. Sorry about that. Yes.
Okay,
Because you
so
have to, because you're attaching to that, it's there's more, you've got the tension of the epoxide, but then you've got more space to be able to come in there and attach there. So
yeah. And then the
yeah.
next one is just like a substitution kind of, right?
Yeah, yeah, exactly. And so yes, exactly. Um, yeah, you're just substituting in D, whatever that is, right? So, and I want to also write that these two are your addition elimination reactions. So we started to see those in the last chapter, where you have like addition elimination. I was like, what am I doing wrong here? Yeah, so that's what you're seeing here. And remember that excess means that it's happening more than one time, right?
Right,
Excess
so
means that,
for the last ones, wait, so the chlorine would be coming off and then the oxygen as well? Or I don't follow like
so the last one. So
those two in
the
red.
ester, yeah, yeah, no, yeah, yeah. So remember that the ester is going to come off. This is another similar to our like lithium aluminum hydride or whatever, the lithium aluminum something. Um, it's similar in that sense, right? So we're seeing that we have we're starting with two different kinds of starting material here. So here we just have this chlorine on the end, versus here we have this, it's still a good leaving group, remember? Like OMe, OTE, those are all good leaving groups, right? And so we are still having this. So PHMGB, let me tell, I'm sorry.
It just kind of seems like there's more carbons in the products. Like at least for the
So
first one in red, and I don't know how that we got there.
So this one, because it's happened twice. Remember, we have the excess. We have excess. So that means it's happening 2 times, right?
Yeah, what's happening 2 times?
The reaction is happening 2 times before we do the acid workup step. So ethyl, and then MgBr, right? So we have
Yes.
our ethyl is here, right? And so here's 1 ethyl and there's 2 ethyl, right? So And because we have excess, it's happening multiple times. So, and it's going to be happening to this carbon. That's what matters, is it's happening to the carbonyl. And the,
Oh, I see
yes,
it now.
yes. And so the excess is what matters. But now remember that in this like the ester has a good leaving group. This O ET is a good leaving group. That's all that matters. It's a good leaving group. That's what matters about it.
Yes, I see. I know. I totally see it now.
Yep. And so this is, so here's this one is the reaction here, because this is what's getting reacted with. And so first excess, again, because we have excess, that's why we're getting 1, 2 phenols, right? And because this, all this is a phenyl. Oops.
Yes. Okay.
Sorry, my pen's being laggy. So that's all that means. So that's why we're seeing the multiple. So, you know, if it's helpful to you, draw it out. If you see pH MGBR, you see ET MGBR, right? You know, and this is OET, right? That's what this is. This is OET. So 1, 2, yeah. I'm like, wait, did I do that right? So you know, it's like the same thing is what I'm trying to say. So all that is just it's creating that leaving group. It's adding those. Remember that Grignard, all it's doing is just elongating your carbon chain. You're making new carbon-carbon bonds. Alkane. You're making new alkanes.
Yes.
And so whatever else it drags along with it, it drags along with it, right? In this case, it's dragging along those phenyl groups, right?
Right. Okay.
Does that make sense?
Yes.
I felt like
I see.
Grignard was probably one of the most simple of everything. It's like once you figure out the Grignard, then it's like, okay, this part isn't that bad, you know?
Yeah, honestly, I don't know. For something just like last semester, I felt like the videos made a lot of sense to me.
Yeah, on top of the world, right? And then
And
this
this
semester, you're like,
semester,
wow, I suck.
no, I just this semester, I don't know, like I just feel like I don't have like as much understanding from the videos as I did last semester for some
Yeah.
reason.
Oh, I remember now. Yeah, I understand what you're saying now. Yeah. I
That's why
understand.
these summary sheets are gold, Sarah.
Yeah, I'll do it
Literal gold.
again. And on Wednesdays, I think I told you, and I told her, or I think you were there. I don't know, but I'm gonna start doing that. Oh, I think I made an announcement, but
Yeah, yeah,
I'm gonna start doing the. Yeah, so I did get permission to use those, so that's good. And then I'm gonna watch back over. I'm gonna watch back over when she went over them to make sure that I am catching all the right all the little things, because obviously I don't have a PhD in chemistry. I'm just doing the best. I'm a lowly undergrad too at this point, so
Could have
I'm just doing
fooled
the best I
me.
can. Oh my god. You know, fake it till you make it, as they say, you know.
That's
but yeah. And you know, the next one that you guys have is, oh come on, you didn't load. Jeez Louise, well, I guess it's a
it's
good
the
thing you didn't want to go.
ethers and the
Yeah, so the ethers and the
epoxides.
epoxides, those aren't necessarily fun. No, they're fine. I'm wondering why this didn't upload, because I literally do have it. I added more to it, but for some reason I'm gonna try to close this out and see if that's helpful. Let me see. And open up GoodNotes again and see if it'll reload something different. Nope, of course not. That's annoying. I wonder if, how do I do screen share from my Let me see, hang on 1 second. Let me do the screen share here. Okay, let me hang on. I'm gonna try to open it up on my other computer. Advanced. Um, maybe I would have to. I don't know why this is. I'm gonna see if I could open it up on my other one. iCloud and backup. Hmm. Oh, I have to update this. That's why I'm like, why isn't it? Okay. So yeah, so okay, so ethers and epoxides. I don't have it on the screen right just yet, but yeah, I know you said you didn't get that far into it, so
Yeah,
but a
I'm
lot of
only
it's
like
kind of
part away.
yeah, a lot of it's kind of the one after ethers and epoxides I like when you got your conjugated systems. That one was a little bit better. Um, but yeah, no, there's a lot of reactions, you know, there's a lot of stuff you gotta remember. Let's see, did this work? Yeah, it can be a lot, I know. So, um,
Yeah, well, I will finish the videos on the ethers and stuff. I know you're doing the review thing on Wednesday. Hopefully, I'm not like
yes.
terribly confused.
No,
But
no, you should be fine. You should be fine. I felt like this week wasn't that bad. I mean, ethers and epoxides sometimes can be a little like, but it's just again, it's just understanding the it's just understanding the reagents, reactions, you know. But yeah, other than that, it's not a bad situation. And then the conjugated systems I felt like was fairly simple, just remembering like how things attach, opening and closing of the rings and stuff. So